Hello, everyone. So when we are moving our topic about probability to the end of the summer, we might stop for a while after one more lecture, maybe next week. So we will continue our topic about stat 395 in the next summer. So remembering from last summer to this summer, we are starting with the coin tossing and the dice rolling, and we're moving to some new topic about discrete models and continuous models about random variables. And we have talked about the joint distribution of the random variables of two random variables or more random variables. So right now, we are going to the end of the first part of probability, which is about the single random variable problem. So today we're moving again to the beginning of the journey, which is the coin tossing. So we'll mainly talk about the weak law of large numbers today, which is, relevant to the topic of if you toss a coin infinitely many times, you will almost surely reach the situation that all the coins, you will receive half the results as the head and half result of the tail, and the theory behind it. Okay, so let's begin. So maybe at first we will see some useful formulas by reaching our to reach our discussion about weak law of large numbers. So first one is called the separation of expected value formulas, the lemma 6.9.6. Okay. So as we studied the independent random variables before, if x and y are two independent random variables whose expectation exists, which means like expected value of x and expected value of y there exist, then we can, if we know their expected value exists, then their expected value is equal to the expected value of their product. So how does this happen? So first of all, like it has two possibilities to talk about. First of all, like x and y, they are both continuous, or maybe they are both discrete. So that's the two cases we are talking about. So first, let's imagining about if they are continuous. So what happened is that because it says like we are prove this result in homework 7, but you are not showing what is homework 7. So we're going to prove this here. Okay. So first of all, we can write the result of expected value of xy, right? This is our beginning, and what is equal to is, well, it's equal to, if it's negative infinity to infinity, which is its boundary, and is xy, which is the extra function g. Remember, this is g, which is x times y, and times its, well, how to say, its joint distribution. So it's xy and xy, which is smaller xy to be its realization. This is dx dy, right? This is the first step. And then because of their independent, so by independent we know we can separate the joint distribution by the product of their marginal probability. So it will separate into the form of this one. So it becomes x times the marginal probability, and then times y times margin probability distribution with y, and then dx dy. So now, because they're separated out, we can do one further step, which is we can separate x together and then times y together, right? So that will be our next step. So it's y distribution of y, marginal distribution of y and dy. So this is and what this is, remember, this is just a formula of the expected value of x and the expected value of y. So we have solved, we have reached out this formula by if it is in a continuous situation. So let's talk about the new situation, which means like x and y, they are discrete. I would say it's very similar because we just need to change the calculation of its expected value to a different form. So when it's discrete, it will become the summation of all of the x times xy at first. Maybe I need to write it larger because it's large xy, right? And time is joint mass function, which is xy something, right? So this is our first step. And then what will happen is like, because they are independent, so it's become the sum of x, x times the marginal distribution of x, and then times the y times the marginal mass function of y. Yeah, so the result will, so the process will be very similar, and then we'll end up with the expected of x and y by separating the x content into one summation and y content into another summation, and we are done. So this is the first lemma. It's the separation of the expected value for independent random variable. And the second lemma is regarding its variance. And this is a very interesting story because previously we have talked about the expected value has a linearity, which means like no matter they're independent or not, a list of like the expected value of xi for all I equal to 1 to n, for example, they're equal to the expectation of their sum, right? Become the expected sum. And this happens no matter it is independent or not. But for variance, it's in a different situation because this only holds, the linearity only holds, the summation only holds when they are independent. And if it's not independent, which will move our next topic, which is called covariance. Covariance is the difference between variance and expectation in this sense. Okay. Nice. So yeah, so first we're gonna prove this one. So what we are using is we'll use the lemma 9.6 to prove 9.7. So the first step is like using the definition of the variance. So the variance can be written in the form of this one. This is a definition of variance, which is the square of like this become our new random variable, the summation of many independent random variables minus its expectation, right? This is our definition. And what this will result in is like, well, the first step is like we can do this step. We can first to how to say, because this one is the expectation of a sum of random variables, and by its linearity we can separate this term out. We can separate this out to be here, and then it's like xi minus e xi, expectation of xi, right? And because of the summation, the sigma is the same, we can move it out. So it might need a further bracket to be this one. And now it become very interesting. It's a summation of something. So we can use the binomial formula, the summation of the binomial formula again. So what we can reach out is like we're reaching out is a summation of the direct term, which means it's OI. This can be viewed as A plus B plus C, right? And this is A plus B plus C. And what we have left behind is we have some A squared plus B squared plus C squared, and a plus some like AB or BC something. And A squared, B squared, C squared is just here because they are using the first index, second index, third index, so they are summed up by this direct square. And when I is not equal to J, which means like A not equal to B, B not equal to C, A not equal to C, in this situation, we can form it up in this form. So this will be the many terms here will be in this form, and this case will be in this form. So now we're solving it from a mathematical perspective, right? Okay. And now, so it will reach this form. So the variance of a summation of independent random variable turns into these things here. So it turns out to be the summation of two things. So, and again, let's think about what this happening. So what is this case? This is just the case of the expected value of two terms the expected value of two random variables. So we're going to think about what they are, because we're going to separate them based on the lemma 9.6. So yeah, so we're doing it right here. We're separating them into different form. Separating them into the product of two separate expectation. And the first one, what will happen is like the expectation of xi minus the expectation of xi. So it sounds very weird. It sounds like the same term, exactly the same, because the expected value of xi is a constant. It cannot be changed. So this is a variable, this is a constant, and the expected value of a constant is a constant itself. So this term can be moved out, and the expected value only remains as xi. And just as we observed, their difference, they're the same, so they're different is 0. And similar to xj's condition. And then product of 0 times 0, well, is 0. Okay. So by independence, in the independent situation, they are equal, right? So they are equal to 0. So yeah, so this term is equal to 0, but this term remains the same. And what this term, let's find out, is exactly the summation of the, how do you say, it's a summation of the variance, because if we do one more step, it can become I equals to 1 to n, the expected value of the things inside, right? So yeah, so surprisingly, this becomes the summation of some variance, because the expectation of the difference of the random variable and its expected value is the variance formula. So now it's a summation of the variance, and we are done the proof. So let's sum up what we find just now. So what we have find before is like the no matter it's independent or not, the expectation, the sum of the expectation is the expectation of the sum. And for variance, it is slightly different. Like only when all of this xi, x1, x2, x3 to xn, these random variables, if they are independent, we can do the summation. The variance of the summation will be the summation of the variance. So that's a slightly different, but yeah, if you can check the condition of the independence for those random variables, and you can apply the linearity of the summation by variance as well, just like what we did for expectations. Okay. So now we're moving to our next topic, which is called weak law of large numbers. So first, let's introduce about its formula, its general form. So the law of large numbers contains two versions. It has a strong law of large numbers and a weak law of large numbers. So today we're going to talk about the weak law of large numbers, which use less knowledge from the probability theory, but by what we have learned before, we can already solve it. We'll mainly use the expected value and the variance formula, as we mentioned before, the 9.6 and 9.7 lemma. And we'll also use the inequality we studied before, like the Markov inequality and the Chebyshev inequality, to solve to prove why weak law of large numbers is a reasonable one. Okay. So first, let each xn is a random variable, and xn, when we're writing this form, which means like it's a sequence. It's a sequence of independent, identically distributed random variables, which I have talked before. We can use it as IID. ID random variables with finite mean and finite variance. So notice it's finite, and this is very important when we are doing, as we show it later. So it must be some IID random variables with finite mean and variance. Then for all positive number epsilon, which is like for all very, very small positive numbers, the probability that the difference between this term and its mean larger than a small number is going to 0 when n approaches infinity. So which means like if n becomes very, very large, as n becomes a large number as it indicated in the title, then the difference between its mean, the mean of each random variable and this term, would just be the same. Their difference is 0. Okay, and so let's think about some examples of it. So I think the most easy example to think about is the Bernoulli trials, like the coin tossing. For example, if you're tossing a coin, for like 100 times, you may find out, well, it's 44 head up and 44 head up and 56 tail up. Yeah, it's possible. And so now what's this form is? If it's a head, then it's 1. If it's a tail, then it's 0, and this becomes like 0.44, right? 0.4 minus the mean, which is 0.5, is, well, it's 0.06. It's not very small, but as we increase it to 1 million, it will be very, very small, and 1 billion, 1 trillion becomes smaller and smaller as it should be. So the interpretation is like for large n, the average of identity for the IID random variables is close to their expected value. All right. So yeah, so the weak law of large numbers use one theorem called the central limit theorem, and the central limit theorem is a representation of the weak law of large numbers. So we'll talk about that in the next lecture, and these two are connected with each other very closely. So this time we want only to show why this is correct. So we can start a proof. So maybe first we can show like this term, the term before the minus sign is its expected value is mu. And then we're going to show the variance of this term, the term inside the absolute value. This one will quickly, its variance is decreasing very quickly as n approaches infinity. If these two conditions satisfy, then we can say, well, it must become its expected value and its variance become very small, which means like, well, it's impossible to vary it out to go beyond this boundary. And that is just what Chebyshev inequality says. Okay, so first, let's calculate its expected value. This expected value, first we can use the linearity of the expectation. So we can get a 1 over n terms out. And what we can use is we can use the identity. They're identical. So the expected value of the sum is this expected value are all the same. So we can just use n times mu, which is its mean, to get the result. So it's 1 over n times mu, which is mu itself. So yeah, we have proved the expected value of the term is just mu. Okay, and what about variance? Variance, first we can use the linearity of the variance at first. So remember, if there's a constant term in front of some summation of the xi, well, maybe not summation, but if here is a random variable and there's a variance here, there's a constant term here or a coefficient here, and then the variance will take the coefficient to be square, so it becomes 1 over n squared, because 1 square is just 1, and it will times the variance of the what's remaining here, and just using the lemma of 9.7, and because they are like independent, because they're all independent. Yeah, and what will happen is like we can get a summation term out. So it will become like 1 over n squared times the summation of the variance. And the variance is, we can use the sigma square to represent it from the question. And now it becomes 1 over n squared times n times sigma square. This is because, again, they're identical, so their variance must be the same as well. So as a result, what we find out is like, well, there's summation. This is just n. So it's n squared, 1 over n squared times n becomes 1 over n. And we just write this term out. So it's become here. Wow. What is this term mean? It's like when n becomes a large number, it goes to infinity. And the remembering what we said before is like its variance is finite. So it becomes very crucial here. If it's not finite, it can go to infinity, and n go to infinity, this term is undeterminate, which it means like it can be zero, it can be infinity as well, because it's not limited. But as the variance, the sigma square is limited, which means like it cannot go to infinity, and n goes to infinity, which means like this term go to zero. So variance is going to zero as n approaches infinity. So by the Chebyshev inequality, remember what I said before is like, well, this is the this is the term we are going to figure out, and the mu is the expected value of the term. So it's just the probability of this one larger than the epsilon. Because the epsilon here is already fixed as we indicate. Well, we say epsilon we already find out is for we already like pick a epsilon because it's for all epsilon means like we always pick any epsilon we can choose. So it can be 0.0001, but it's already existed, right? And the variance, and by the Chebyshev inequality, if you can still remember or recover from the previous class, and this one becomes the probability that any random variable go, like it goes beyond its expected value by the value of this term, which means larger than epsilon here. It's the variance of this random variable, and it's over this term square, which is the epsilon square. Okay, and just remember we have used the assumption. We have the assumption that the mean is also finite. So this is finite. This is finite. Okay. So this is n. This is not mean. So this is finite. The sigma square is finite, and this one cannot go to zero because it's already fixed, and n goes to infinity. So the denominator goes to infinity and the numerator goes to some fixed value. So it goes to zero as n goes to infinity. So yeah, so which means like we have proved this one. So the probability of this term inside go to zero as n becomes a very, very large number. Okay, and then let's see some examples of how to use the weak law of large numbers. So just as we indicated before, we can use the coin toss to mimic the process, and we can also reversely, we can also use the weak law of large numbers to indicate the result of the coin toss. So suppose that you have a coin which you do not know whether it's fair or biased. So you can answer the question by flipping the coin many, many times, 20 times, 50 times, or 100 times, and count how many times you observe the head occurs instead of a tail occurs. So the number of the heads divided by total number of coin toss is, if it's far away from 1/2 or far away from 0.5, this can be concluded as a bias because because maybe their expected value is not 1/2. So why this actually works is based on the weak law of large number. Because as we indicated here, if n is going to infinity, then it cannot be very separated, or separated from its expected value. So maybe if we get it's closer and closer to 0.7, which means like, well, it's almost surely that its expected value is 0.7, not 0.5. Okay, so how can we set up this question? It's like we can use the indicator function as xi equal to 1 if it's head and 0 if it's not head, which means it must be tail. And then it is a Bernoulli distribution, and the expected value of xi is equal to the probability that has occurred. So which means like we can use the weak law of large numbers to use this formula, the probability that the expected value of xi that go beyond the probability that had occurred larger than epsilon is 0 as n goes to infinity. So if we toss a coin, infinitely many times or a very large number of times, this term will gradually become closer and closer to the expected value of the probability that had occurs. So yeah, so we can just calculate the had how many times had occurs divided by the total times we toss a coin to get the p to see whether it's a fair coin or not. And also, example using the geometric probability is like we can use a geometric shape to determining the value of pi, which has been a very long problem from ancient times. Like people cannot decide the exact value of the pi. So, uh, very intuitive solution is like we can use the Monte Carlo integration or Monte Carlo method for simulation to mimic its value. And we'll use the weak law of large number here again. So what the question set up is like we have a unit square, maybe not a unit square, but double the size of a unit square. Like it has so this is one, this is one. So it's not a unit square, but a square with the area of 4 and with size 2. Okay, and that's the that's the setup. So its area is 4. And now we're estimating pi. And we draw a circle in the center. And as far as we know, um, like this circle has a radius of 1, right? Has a radius 1. And we know like the how to say the diameter or the area is calculated by pi r squared. And also it's pi 2 pi r. So we can get how long the circumference it is, right? Okay, so this is set up, and then we are randomly selected some point inside this square of area 4, and we'll see how likely it is inside these circles, and then we can figure out the pi. So let's indicate the area D. Area D is this circle, the circle with area 1. Not with the radius 1, with diameter 2. And then you can set up like well, we can use the pi. We can estimate pi using this term. Why? Because this term is indicated as 1 over n, which is how many times the point is selected, and the point selected is a uniform distribution inside this area 4. And if it's inside the D, we say it's 1, and if it's out of the D, which means the 4 corner here outside the circle, is 0. Okay, so by the weak law of large numbers, this was very close to the expected value of itself. And the expected value of this term is just xy is belong to D, because it's a uniform distribution over this square of area 4. Okay, so and then this one can also be represented as the integration of the area. So if you study the calculus before, how you can determine the area of this one, it will become the upper bound minus the lower bound by the function is indicated, right? And the function is indicated is 1. It's just how to say we can use the 1 minus y squared from negative root square of 1 minus y squared to indicate that. Well, you can also use the polar coordinate if you want, but if you have not studied a polar coordinate, you can also use the rectangular coordinate, which will use this formula, which will use this transaction. Yeah, this makes it very complex, but because it's just 1 in the center, the integrals is 1, so it will be easy to calculate as 2 times this one, and it's going from, and then first of all, it's calculated by x, right? So the x term is going from this boundary to this boundary, and then as we indicate its boundary, we are going from y, and y is from -1 to 1. And then we calculate out is pi over 4. So yeah, so this is the expected value, or the expected value of this term, or the probability that xy belong to D. So how is this important? How is pi over 4 important? This is because like pi over 4 by weak law of large numbers is very, very close to this value. And here, like 1 over n is a non-number. So 4 is a constant, n is a constant. And this value is also constant because every time you select a point, you know whether it's inside or outside. So if it's inside, you add 1, and it's not inside, you not add 1. So this term is null. 4 is null. So we can use pi. So all these values can be used to solve pi. So pi is very close to the value of 4 over n times this indicator function's sum. All right, so that's our discussion of the weak law of large numbers today. And we'll move to the next topic, which is called covariance and correlation. And honestly, like covariance is a topic in 395, which is in the second series of probability. So I will not talk really into details about how the covariance calculation and its formula, but I'll mainly talk about how it means and what's the difference between covariance and the independency. Okay. So if we know like two random variables and x and y, as we talked about at the beginning of this lecture, we say, well, its sum can be viewed as the expected of the sum of their expected value as well, no matter if they are independent or not. But what about variance? Variance is different because variance, as we can see it from the beginning. Yeah, here, variance is equal to its sum of its variance plus this term. And if it's not independent, this term might not be 0. It can be a number. So it's the sum of the variance plus some term, plus this term. And what this term indicates here is what we call the covariance. So, and because like I not equal to j, there have two symmetric terms, like first is ij and then ji by the like they can be ordering in two ways. So it's 2 times this value, and we can divide it by 2 always. And half of this value of what's remaining to be the sum of the variance is called covariance. Okay, so the definition of the covariance is easy. It's just the form of if there's 2 random variables, and we can define the covariance is defined as cov xy, and this is equal to the expected value of x minus its expectation times the y minus its expectation. And there's also one thing called correlation coefficient, which is usually denoted by the Greek letter rho. And rho xy is equal to covariance of xy divided by the root square of variance x times the root square of variance y. Okay, so and we'll talk about this formula and how it's calculated in details in next summer. So here let's talk about some of its properties. If x and y, if they are independent, then x and y are uncorrelated. This is for sure, which means like anytime that we can observe f, if we have known the fact that x and y are independent, so we can use a graph to show it. This is x and this is y. What their independent means, like all the points that they are randomly occurs in the plane. So yeah, this is a randomly or independent form. There's no dependency you can see like x is from y, and they are not correlated as well because it's just random, so they are not correlated. But being uncorrelated doesn't mean like they are independent. For example, a good example is it's like that. This is x and this is y, and if you can draw all the points in a unit circle here, it's uncorrelated at all. Because correlation, which means always means like they have a slightly like a linear relationship here. Like this means they're positively related, and this is, and if you observe something like that in this band, which means it's negatively correlated. But if it's all point in a circle, it doesn't have this shape or this shape, and they are uncorrelated. However, you cannot say they are independent because X is really dependent on Y, and they're dependent by the function X squared plus Y squared equals to some constant A, right? So even it's uncorrelated, we cannot say it's independent. But if two variables they're independent, we can always say it's uncorrelated. So that's the fact here, and the difference between the correlation, like the covariance and independency. And also this term is calculated in this way. It's between -1 and 1. And this is independent of how their coefficient changes. So which means it's invariant. It's scale invariant. It's still different. So if there is exists a or alpha is a constant, and the correlation coefficient of a constant times y and y, constant times x and y is equal to x, and the constant times y and is equal to xy. So timing any constant or coefficient to a variable x and y doesn't change this coefficient value. So which means like it's a good indicator. As you can calculate, if it's very close to 1, -1, it means like it's strongly positive or strongly negative correlated. And if it's close to 0, which means like it's weakly correlated or not correlated in theory or in fact. Okay. And there's some lemmas about this point as well. Like if we can pick two random variables x and y, their covariance is equal to the variance. Or we can say like its covariance, this covariance can calculate in xy minus expected value of x and expected value of y. And this one, well, we'll talk about in next summer in 395. And this one is like if x, well, covariance is usually calculated as like x and y. When x and y, they're different, but when they're same, it's the same value, it's just become the variance. And this is, well, I think this is intuitively because x and y, they are, if x and x, if they're independent? No, they're not. No, they cannot be not independent. They must be dependent on each other, and it's 100% dependent because they're the same. So it must be variance x because this correlation coefficient must be 1, right? And if it's 1, and this value will just become just equal to its denominator, and its denominator now becomes the variance of x times the variance of x root square, which is variance x. So the covariance will also be the variance of x. Yeah, so in the last part, let's introduce a very useful inequality, the Cauchy-Squartz inequality. Okay, so this inequality, how it can be used? It is used to bound some values in a plane. For example, this one is very useful in complex analysis when we're considering how a complex values modulus cannot go beyond which point, which means like, for example, x is the real part and y is the imaginary part of a complex number, and its expected value of x times y, it will becomes, it's smaller or equal to the root square of its modulus of x and the root square of a modulus of y, its imaginary part. So this is how it is used in a complex analysis, very obviously, and also it's used in nonlinear optimization when we are doing some like when there's a topology spaces, and so let's say a topology spaces in 2 dimension, and there's an open ball here. Maybe this is a closed ball and an open ball here. And we are talking about closed and open balls. Well, I'm gonna say what's the distance to its boundary, from its center to its boundary, or from a point to its boundary. It must be smaller or equal to something here. And this is also called triangular inequality in topology. Yeah. So after we realize how important the Cauchy-Squirazzi inequality is, let's talk about how what is formed and how it is used. So if there's two random variables x and y, with the expected value of x squared is smaller than infinity and expected value of y squared is smaller than infinity, then the value of x, y, their product will be smaller or equal to the root square of each of the expected value of x squared times the value of y squared. And this inequality have equality form when they're equal, right? And the equality holds only if and only if there exists a and b in real numbers, not both equal to 0, and a times x plus b times y is equal to 0. All right. So let's first prove this form. Let's first prove, well, it's smaller or equal to this point, and then we'll find out why is the equality will occur only in this form, only in this case. So let's first assume like x not equal to 0. And without loss of generality, we can also do it when y is not equal to 0, as x is not equal to 0. Well, they can be same, because when x is not equal to 0, and we can just change x into y and y into x, and y is not equal to 0 is equal to x equal to 0. So the without loss of generality can be used here when we can. So which means like we can only discuss the situation x not equal to 0. And we can define function here. We can define function fa is equal to the expected value of y minus ax squared. Then, because x, y, they are random variables, so their realization here must be real numbers, and a is a real number as well. So the square of the real number is always non-negative. So fa is a non-negative number. And we can expanding this form out. So the first term will be ey squared and minus 2 times y ax squared. And x, y are variable inside expected value, and a can be extracted out. Similarly, ax squared is equal to a squared times the expected value of x squared. So fa, this formula defined here, can be written in this form as well. And then by using the knowledge of calculus, we might be interested, or like we are required to find out its minimum point. I know it's a bit of like most people will not consider this point. Most people will say, why we need to find a minimum point here? So I would say that's the wise of how mathematicians solve the problem. And honestly, 99% of people cannot is not able to prove this one when think of, well, I can use the minimization of a quadratic function. So that needs like very empirical studies. So yeah, when we minimize that, we use its first derivative, which is can be calculated as like because it's a function of a, and this no way constant removed, and this will be the -2 times the expected value of xy, and plus 2a times x expected value of x squared. And because we want to minimize that, we want to find when it becomes 0, right? When it becomes 0, it's easy to find out. Like first, remove this part to this direction, so it becomes 2a times expected value equal to a -2 expected value of xy, and 2 can be cancelled out, and a is remaining here. So a becomes the expected value of xy divided by expected value of x squared. And just because x is not equal to 0, as we assume here, x is not to 0 or y not to 0, so this term it's not equal to 0. So it's a defined term for A star. Okay, so A star is the minimal point we find it here. And because A star is a minimal point, or well, like A is satisfied in the minimum point by this function, then we can plug A star back to the original function, or maybe this function. So we can find out the inequality here, because we already have a smaller or equal to. So 0 is smaller or equal to f A star by this fact here. And then A star, we plug A star back. So E y squared doesn't have A, so it keeps the same. So let's write is E y squared, right? And the first term is like -2 times, because now A becomes A star. So it's E expected value of xy squared. And the denominator is expected value of x squared. Yeah, it doesn't change, so it's x squared. And this term becomes plus this square, but we'll square this term, right? This is squared times its value of x squared. So it's canceled out. One layer of the expected value x squared, and this will remain here as y2 squared. Here, yeah. So that's the result. And what's the difference here? It's like, well, we can see here the expected value of y minus 2 and plus 1. These two terms are the same. So we can just by deleting this term out, and plus 1. So it becomes -1. So it becomes this form, right? So now we have reached this step here. So this is what we got from last time. And this one will be interesting because 0 is smaller or equal to this one. And we can move this term to here, and it becomes like this term is smaller or equal to this one, and times the expected value of x squared back. So it becomes this one. And this one we can, how do you say, like we can do a expect value again. Okay, so there is a written, it's error here because this is square, it lost the square. So what we do here is like we do the square root. So this one becomes the expected value, and this one is like using the product law of the root square. So it becomes this form. So we are solving the Cauchy-Squartz inequality totally. Okay. Now regarding in what cases the equality occurs. So first, like so here we said the equality only occurs when ax plus by equal to 0. So we just assume this is the case, and a, b are real numbers. And what we have here is like the fa equal to 0. It becomes it's become the expected value of this term is equal to 0. And now, in what cases this one is equal to 0? There's only one case, because this one is non-negative. So y minus a times x must be 0. And this is indicate that y is equal to ax. And which means like, well, this is the only case. And this one can also be written in the form like ax plus -1 times y equal to 0. So a is any real number, and b is -1. So this is the only possible form that will lead to the equality. Cool. And yeah, there's also another further discussion about the covariance and its correlation coefficients range. We are using this Cauchy-Squartz inequality to prove why the coefficient of correlation is between -1 and 1. So we have the correlation coefficient is by its formula, by its original formula, is equal to the expected value of the product of x and y, right? These two terms here. And by using the Cauchy squash inequality or CS inequality, what we can find out is like this one is a summation. It's the expected value of two summation. Is the expected value of two product, and the product can be separated out by adding square and using and by a root square outside here. Okay. All right. And what is two terms inside? This one is the variance of x, and this one is the variance of y. So yeah. So the expected value, so the absolute value of covariance of x and y is smaller or equal to variance of x and times the variance of y by its root square. So just recover the rho xy. Its formula is the root square of variance x times the root square of variance y, and this is the covariance of xy, right? This is its formula, and this absolute value is smaller or equal to this one, which means like the expected value of xy of its coefficient of correlation will be smaller or equal to 1, because this one is smaller or equal to this one, and this one must be positive. As a result, when we get out of the absolute value, it's like -1 smaller or equal to xy smaller or equal to 1, and then we are solved. And similarly, there's also a special case regarding this inequality. It's like when the equality holds, which means like the correlation coefficient is equal to 1. And this only happens when a times x plus b times y plus c is equal to 0. So this is the case here. So we'll show that the correlation coefficient is equal to 1 if and only if this one occurs, right? So first, assume we can write this form directly out, because this is assumption. So a times x plus b times y plus c is equal to 0. And this is equal to, we can rewrite this form by using x to represent the remaining things. So x is equal to this one. X, we can use y, some coefficient, some constant with y to represent x. So now we can write the correlation coefficient between x and y by only with y or only with x, probably. So this is the correlation of x and y. And because like the covariance, we consider covariance for linearity, and then the constant term can be removed, and we can only consider v over a, and this is v over a times this one. And the variance, well, variance is also regarding only for, sorry, so the variance is only regarding the coefficient before the variable, and it's not considered when we are talking about coefficient. So the variance of y, yeah, so let's talk this in a little bit detail. So variance of y is equal to maybe no. Okay. So variance of x is equal to the variance of negative b over a y minus c over a, and this is equal to the variance of negative a under by, and it's equal to a over b square y, right? So this is the result. And when we consider the root square of this one, so it's the root square of this one, and it becomes b over a times y times the y times the root square of y, variance y. I mean, yeah, variance of y, variance of y, variance of y. And this one is a covariance of y and y. And by the lemma we just mentioned above, this one is the variance of y times b over a. So they are just equal and becomes 1 in the end. Yeah, so that's all we have talked about today. And it's almost 1 hour. It's a very long one. So next one, we'll talk about the last lecture in this year, which is the central limit theorem. And it's another aspect about the weak law of large numbers.